Projectile motion. So what is a projectile? Well, a projectile is an object. It's the object designed to be fired from a cannon or some sort of object that is launched. And there's two different ways that you can launch it. So here, as you can see, there are three different paths, right, that the object can take whenever it leaves the cannon. On our red dotted line, we have a gravity-free path. So in a perfect world where we didn't have gravity, of course the object will continue going in a straight line, right? Newton's first law, an object in motion will stay in motion unless unbalanced forces, aka gravity, acts on it. So without that gravity, the object would have that perfect inertia and just keep going in a straight line. But of course we have gravity. If the object just rolled out of the cannon, it would take this black path. So that's the path due to gravity alone, so no launch. But when objects are launched from a cannon, thrown off a cliff, whatever the case may be, it actually takes the path of this blue line. And as you can see, it's curved, right? So this is the path of the projectile motion whenever it's launched out of this cannon. So what is projectile motion? Well, it's when objects follow a curved path like we just looked at because it is moving horizontally. So remember horizontally, changing your x values, or vertically. So vertically changing your y values simultaneously. So both are moving. The x values and y values, you're changing them both. The vertical motion is analyzed like a falling object. So remember, we've already done falling objects. Falling objects is just that vertical motion. So now we're going to be adding in the horizontal motion. Fun stuff. So again, the horizontal motion follows Newton's first law because the horizontal motion, it is constant. It's a constant motion in a straight line. So we're going to look more into that as we keep going. So there are two types of projectiles. One type is an object that is launched at an angle. So it could be any kind of angle. It could be 90 degrees, 60, 30, 47. So any kind of angle that is launched, that object is again going to have that curved path. So as it's going up, 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 it's fighting against gravity. It reaches this top point where the velocity is 0, and then gravity pulls it back down. Or, like with the cannon scenario, you can have horizontally launched objects. So that means you're trying to launch it horizontally, but of course gravity is pulling it downward. So it also has that curved path. So two curved paths because it is projectile motion. So let's look more at objects launched at an angle. So maybe a person launched the ball, and this is our starting point down here. So, you see a lot of arrows, right? So these arrows are called vectors. So remember, a vector tells us both the magnitude and the direction, okay? So vector has both magnitude, the size, so how long is the arrow? Longer arrows indicate a greater magnitude, and then the direction. You also see Vy and Vx. So Vy is our vertical component, and our Vx is our horizontal component. So as we look at these projectile motion, yes, it has both vertical and horizontal components, but we like to look at them separately. So first, let's look at our horizontal component. So just the Vx. So as we're looking at Vx, you should see Vx here, here. These are all of our Vx components. And you'll notice that all of these labels match a red arrow that is all pointed the same direction and the same length. So, just by looking at all of these Vx vectors, or our horizontal velocity vectors, you'll notice that every single vector is the same length, so it's the same magnitude, and the same direction. So that means our Vx, or our horizontal velocity, is constant, right? It is constantly going to the right and about that size. So same size, same direction. So if we were going to assign a number to our horizontal velocity, let's say that we launch it and our horizontal velocity was 5 meters per second. That means that at every single position as that ball moves, the horizontal component is always going to be, sorry, it's hard to write and talk, is always going to be 5 meters per second. 5 meters per second. So it doesn't matter where the ball is on its path, going up, going down, the velocity and the horizontal component is always going to be moving forward 5 meters per second. Okay, so now let's go ahead and look at our vertical component. So again, we're launching a ball upwards at some angle, and eventually the ball reaches this tip-top position, right, where the velocity is 0. We already know that. And then it has to come straight back down. So let's start at the beginning where our ball is launched and look at our Vy component. Look how large this vector is. That means that it is some sort of really big component, right? So let's just say that it's 30 meters per second that we launch it. We're launching it upwards at 30 meters per second. Next, at our next position, here, the ball is located, and again, our horizontal components are not changing. Look at our vertical component. This arrow is longer than our horizontal component still, but it's not 30 meters per second. Well, technically, it's fighting against gravity, negative 9.8, or we'll just round to 10 for these examples. So the velocity here is probably close to 20 meters per second. So, as you can see, our velocity is decreasing. So we're still moving in the positive direction, up. However, we're fighting against gravity. Gravity is slowing us down. So we're going from 30 meters per second to 20 meters per second, slowing down just a little bit. Looking at our next position, the ball located here at position 3. So you'll see that the vector is even smaller than before. So 10, 20, fighting against gravity still. So it's probably close to 10 meters per second. 10 meters per second. Then, at our next position, position 4 at the very top of the path, we know that our velocity is 0. This is the exact moment where the velocity is 0 and the ball is about to change direction. Because now the ball is not going any higher than it is. It's no longer going in the positive direction. It is now going in the negative direction. So if we look at the ball in this position here, position 1, 2, 3, 4, 5, you'll notice that the vector is the same exact size as it was over here. So you'll notice that these vectors are the exact same because they're at the exact height. So that means that if it was 10 meters per second over there, it's going to be negative 10, because now we're going towards the negative direction, going down, negative 10 meters per second. All right, go into position 6. You'll notice that it matches this position over here. Same height. So our vectors are the same length, meaning if over here the vertical velocity was 20 meters per second, over here it is now negative 20 meters per second. All right, and then our final position. So we launched it and it landed in the same exact position. So again, we have that symmetry where our velocity to start with for our vertical component, we launched it at 30 meters per second. Now our final position when it hits the ground, it is negative 30 meters per second. All right, so in words, the motion occurs in 2 dimensions. So when we're talking about projectile motion, it is 2-dimensional motion. We are talking about vertical and horizontal components. For the initial vertical velocity, so remember vertical, we looked at all of these red arrows going up and down. You'll notice none of these vertical velocities, except this one up here, is 0. So the initial vertical velocity over here is not 0. And it changes. You can see that it changes. You have a huge arrow to start off with, kind of a medium size, a smaller size, no arrow because no velocity, back to small, back to medium, back to large. So it changes. Our vertical component changes, right? Because at first we're going up, 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 fighting against gravity. Then we're going down, 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 and gravity is pulling us faster and faster towards the center of the earth. All right. Now we're going to look at the horizontal velocity. So the horizontal velocity is also not zero. So they're both not zero to start off with. Our horizontal velocity is whatever our launch velocity was. So in this case, we said it was 5. Our horizontal component remains 5 for every part of our journey because our horizontal velocity remains unchanged. There is no horizontal forces acting on the object. There's no gravity in the horizontal. Gravity doesn't pull us left or right. So our horizontal velocity does not change. And the time and the speed, as we already mentioned, is symmetrical as long as the launch height, so the launch height and the landing position are the same. So they were the same, so we did see that symmetry, and we already looked at it. We already saw that symmetry. Okay, next part. So we're going to be looking at horizontally launched objects. So again, maybe there's a cannon here that has launched an object. So again, we're going to be looking at these vectors. The Vx component is going to be horizontal, and Vy is going to be vertical. Okay, so first let's go ahead and look at Vx. So let's look at our Vx component. I'm going to trace over those green arrows with green. So here we have a Vx, we have a Vx, we have a Vx, and a Vx. You should see a pattern, right? The arrows are all the exact same length. So maybe it's 10 meters per second, 10 meters per second, 10 meters per second, 10 meters per second. Okay, so as you can see, again, our horizontal velocity, our left-right horizontal velocity, does not change. It is 10, 10, 10, 10. Okay, now let's look at our vertical velocity. And as you can assume, yes, it changes. So at first, no arrow. There is no vertical velocity whenever you're first launching an object. But then after its first second, you do have an arrow. Small, but still an arrow. So maybe this is 5 meters per second. Then it gets larger. So maybe this is 20 meters per second. And again, I'm just making up numbers here just so you can see the pattern that the vectors are increasing in size. And maybe this one is 35 meters per second. So as you can see, our vertical velocity, our up-down velocity, is increasing. And because all these objects are moving in the negative direction, because they're going downward, these are all negative values. So for our vertical velocity, we are increasing. The ball is moving faster and faster and faster as it falls down because gravity. So let's look at just the word formatting. So here's your notes. The initial vertical velocity, so here, the Vy, because we're talking vertical, is 0. But it does increase as the object falls due to gravity. And we already saw that because look at the vectors. The vectors are increasing in size. So our vertical velocity is increasing. Gravity is pulling it faster and faster. Now let's look at our horizontal velocity. So our initial horizontal velocity is not 0. So when you look at our start position here, we do have that horizontal vector. There is a horizontal vector and it remains unchanged. Unchanged for the duration of the flight because there are no horizontal forces. So again, there is no gravity that pulls us left or right. Gravity only pulls us downward. So nothing affects that horizontal velocity. It remains the same. 10, 10, 10, 10. And just looking at our equations, these are all a review. These are our free fall equations. These involve the vertical component of motion. Now these are new-ish, same pattern, but these include our horizontal motion. So these have x values. You'll see that there are x values embedded in there because our free fall was y values, the vertical motion, we had y values here. So you'll see the pattern.